One type of circuit that we have yet to look at, and it's a little more complicated, is what's known as the complex or the combination circuit. If you're an electron passing through this circuit, you must go through R1, you have no choice. You must go through R5, you have no choice. So we say that those are wired in series since there's only one pathway through those two and you cannot go around them. But with R2, R3, and R4, you do have some options, which means parallel. So this combination circuit or complex circuit has elements that are in series, but also elements that are in parallel. It's a little bit more complicated to try and analyze this. So before we do the entire analysis, we're only going to analyze the parallel section, and I'm going to show you a trick which is very helpful when trying to analyze these circuits. It's known as Kirchhoff's junction rule. So we're going to ignore the entire first half of that section. Let's assume that we actually analyze the circuit and we have determined that 6 amps of current comes out of the battery, passes through R1, and then splits up in those 3 branches. So we're going to ignore R1, R5, we're going to ignore the 40 volts. We're just going to assume that we've determined that 6 amps is coming in, and Kirchhoff's rule applies just to a parallel section like this. So for the time being, we can ignore that section. We'll add that back in another video. So the interesting part is that the current will then split amongst these 3 resistors, and it will not do so evenly. We can't assign 1/3 of the current, or 2 amps for each, because they have different resistances. So now we have to understand how we can determine the current in each branch if we actually have varying resistances. So we know that 6 amps goes in. We also know that when it comes back together, 6 amps must go out. You can't lose electrons. We have to figure out what goes on in the middle there. So the way I would suggest doing that is you calculate the proportionality of all resistors relative to the largest resistor, and I will show you exactly what I mean by that. So what we're going to do first is we are going to put 7 in the numerator of 3 different fractions, because we have 3 different branches. In the denominator, we are going to put in the resistance of that branch. So you'll notice in the numerator is a 7, because that's my largest resistor, and in the denominator, it's the resistance of each of those branches, 7, 2, and 5. So we find that proportional to itself, a 7 ohm resistor has a proportionality ratio of 1. It's 1 times as big as the largest resistor. 7 is 3.5 times larger than 2, and 7 is 1.4 times larger than 5. So we're finding a proportionality constant. Basically, how many times larger is the largest resistor relative to the resistance of the individual branch? The next thing we're going to do is we're going to apply X as the unknown current. So you'll see that instead of 1, 3.5, and 1.4, I just added an X next to each of those. So the current going through each of those branches will be 1X, 3.5 times X, and 1.4 times X respectively. I'm then going to sum all of those currents. I don't know what each individual current is, but I know that if I add all 3 of those up, it must equal the 6 amps that enter the branch, and also obviously the 6 amps that left the branch. Now I can just analyze this algebraically. If I add up those 3 values on the left, I find that 5.9 times X equals 6. Solving by dividing each side by 5.9, X must be 1.02 amps. So now you'll see I have 3 of these constants, these proportionality ratios, and 3 branches, and I know what each one will be. In the first case, it's just 1 times 1.2, so that tells me that I have 1.02 amps traveling through the branch that has the 7 ohm resistor. To figure out the second branch, it's going to be 3.5 times larger. Since the resistance is 3.5 times lower, I'll have 3.5 times more current. So 3.5 times 1.02, which was what X was, gives me 3.57. So I now know that in the second branch, 3.57 amps of the 6 will pass through that branch. And I can do the same for the final branch. It's 1.4 times 1.02, which gives me 1.43. And I know that 1.43 amps will travel through that third resistor section.